And so he will talk about when to use when the best model for pandemic are the simplest, right? So, okay, please start.
Well, I'm happy to be able to talk to you all about this. One of my concerns, having watched epidemics for many years, is how do we influence the politicians who make policy? And that was sort of my emphasis, or our emphasis of this paper we published in MDPI biology. But I would extend that. And when we see the general public's response to this epidemic right now, we see, for example, France, Italy, and Spain have controlled the disease, the outbreak, very well, and then it escaped and went out of control. And in the United States, there are many areas where there was never any control. And people just behave somewhat stupidly. And so I want to address the point of what would we like the people to know about epidemics? And so my emphasis is on the simplest models of epidemics. Now, when I talk about the simplest models, you can all the simplest models can only do the simplest things. That's not true. And I will explain how the simplest models can be used to handle quite complex things. So, as I say, in the past week in the United States, the case rate has gone up by 48%. So the transmission rate from, if we take, I will take the generation time from person to person as being about a week. And so we're getting here a transmission rate of 1.48 at the current time. And so you can try to remember that. And so there's a story, a parable. Parables are often in the Bible. They often involve rather disastrous things. A parable about a fellow who's living near the sea and a hurricane is predicted to come in. And there's a knock at the door, and he answers the door and he says, the officer says, you have to leave because there's going to be a big storm. And he says, no, I will trust in God. And he stays. And the water comes in, and it's so much that he goes up to the second floor. And a boat comes by and says, quick, jump in the boat. I will save you. And he says, no, God will save me. I have faith. And the water goes up higher. He goes up to the roof, and a helicopter comes by and says, climb into my helicopter. I will save you. And he says, no, I have faith. God will protect me. And he drowns. And he goes up to heaven, and he's complaining to St. Peter, I had faith in God. And St. Peter says, look, we sent an officer to your door that you ignored. We sent a boat to rescue you. We sent a helicopter to rescue you and ignored it. And you drowned. Now, that story seems to me to be a parable for the last 20 years. First, we had sent to us SARS in 2003. And I remember the newspapers and how it was spreading to the United States and in small numbers, and Canada. And then the second wave came with the novel H1N1 called the swine flu. And I talked to people who lived through this, and they forget it completely, because while initially it was described as having a high death rate and being quite infectious, it turned out to have a mild death rate. And so they forgot about it. Okay, so we move up to the roof and we have Ebola. And Ebola was a truly scary disease. I mean, it affected Liberia and 2 surrounding countries in high numbers. And it was in 14 of 15 jurisdictions in Liberia, so it was spread throughout Liberia. It was in the capital of Monrovia. And there's a peninsula in the capital of Monrovia where they actually isolated the peninsula and people couldn't get out and there were riots. And I said, how are they ever going to contain this? And a couple of cases wound up in the United States. A nurse in Houston, I think, died. And somehow it was controlled. And so what's our response to these 3 epidemics? Basically, I mean, as a society, not as epidemiologists, but as a society, basically, epidemics are easy to stop. That's the conclusion that people seem to have watched. Now, me, about 4 years ago, I went out and I bought a lot of N95 masks because I said, hey, I'm not going to be able to buy them when the next epidemic hits. And I mean, what else could I do to protect myself other than just buy some masks? So in any case, when this one is over, are people going to behave the same way? What we seem to be seeing is when the first wave hits countries and they control it, they say, well, we don't have to do much testing. We don't have to do much. You leave it up to the local politicians, and the local politicians are by and large often unable to deal with the problem, and it breaks out. So I'm going to switch to coronavirus, and I want to talk, well, not directly, I'm going to talk about seasonality. And so we're all been told that this disease might be seasonal. That is, the contact rate might vary seasonally. And so how much does it vary? Well, wait. So I want to say here that the contact rate in China was initially reported to be roughly between 2 and 3. And one of the things, of course, we didn't know how good the reporting was and how consistent the reporting was, but nonetheless, that's what we had, is people were estimating it between 2 and 3. And this particular epidemic curve that you see here, that is the rate, the exponential rate is significantly bigger than 3, because the number of cases grows by close to a factor of 1,000 in a month, in a couple of weeks. So now I want to talk about seasonality and seasonality of transmissible virus diseases. And we published a paper on estimating the variability in the seasonality of these 3 diseases. Also polio, but polio is highly infectious in the summer unless otherwise. But I don't want to talk about why these diseases are seasonal, because the amount of seasonality is so small that it's easy to account for it in many ways, through dry air or wet air, or changes in transmissibility of the contact rates just people seeing more people outdoors, but maybe they're outdoors, so they're transmitting it less. Who knows? So in any case, London, who's a physician, and I went to New York and we collected their data. This is a huge amount of data. We had much more than was shown here. We had it by region of New York City. And so I'm going to be telling you primarily about measles. So measles is a childhood disease which is known to be significantly more infectious than the common cold. But in any case, what was happening is that there were epidemics pretty much every other year. And so if you wanted to take this period of a few years where it was big epidemic, little epidemic, big epidemic, little epidemic, you could average the high years and average the low years and basically get a periodic 2-year epidemic to represent what's going on. And so here's what we did. We got this periodic with using perhaps 20 or so years of data from New York City. And the minimum of the epidemic was 60 people, and the peak of the epidemic was 7,000. And so if you assume that basically you got susceptibles entering the population at all times, these are mainly kids, and they get infected and the susceptible population drops so you can see up here, we have a big peak epidemic and the susceptible population drops. So make a long story short, we can say that this, we basically get a transmission rate, which looks like this. So this is your beta, your contact rate, and you can ignore the scale because we were not interested in trying to talk about specific person-to-person contact rates, just how it varied. So what we found, so you can see that it's hard to say what you even mean by how much fluctuation is there between the winter, and here December spikes, and over here November spikes, and then in July and August it's very low. But these peak aren't really representative. So we could say, suppose we take this red line as being the winter level and this as the summer level. Now you might adjust these numbers up or down, but it gives you a rough ballpark as to what to expect. And so this is a 2 to 3 ratio. So that in the winter, it's 1.5 times as infectious as in the summer. In the summer, it's 2/3 as infectious as in the winter. So that says that if you can control, if it also holds for coronavirus, and we have no reason to think it would or wouldn't, but we got the same kind of results for measles, mumps, and chickenpox and polio in terms of seasonal variability. So if when you were in the summer, you were getting control and the contact rate was about 1, this would mean that in the winter, you would have contact rate just naturally going up to 1.5. And again, we're not talking about specific belief in these particular numbers. And the United States was sort of in control of the epidemic in the summer. And the numbers I just showed you said that the contact rate went up to about 1.48. That is the multiplication factor from per week to week. So here's what's happening in the United States. right, these numbers, these are the changes from a rise in the new cases from the week before in various states. And it'll fluctuate a lot from day to day just because of the nature of the statistics and the collection. Here, Iowa is 56%, South Dakota is 1%, but that's just because 2 days in a row, there was basically no change. Well, I guess I should say a week in a row, there was no change. And the governors in some of these states are saying, oh, we don't want to do anything. It's up to the people. And in the lowest rates, we're also seeing very similar increases. And so this might be consistent with states that had policies which were controlling it, and beta was less than 1 in the summer, and now, due to seasonal change, this is about what you would expect. In the United States, when the epidemic was controlled due to the lockdowns, beta just dipped down a little bit and below 1. Here's an example just of the difficulty of talking about these numbers. And so here we have Iowa is a state in the United States, and somehow in the last 2 weeks, it has shot up a bit. It had been growing slowly. And so over here, we can look at the corresponding beta. And so beta was here, was near 1, and then it shot up to 1.5, and it's 1.7 perhaps. The point is that this just shows, or these things just show you the variability of these numbers. And when we calculated the contact rate, seasonality, we're talking about a city of 8 million people. And we're talking about looking at the data for 20 or 30 years and condensing it into one number. Now, when we talk about epidemic models, we can throw, oh, we should include the following factor, whatever. And you don't have 20 years of data on this kind of a thing. You can't measure the numbers in a laboratory. You can't measure the transmission from 30-year-olds to 70-year-olds in the laboratory because we don't know what the nature of transmission is. And the World Health Organization has been debating the nature even in crude terms. If we look at the United States, in the past week, the cases rose by 34%, which means beta was about 1.34. Okay, so of course that's putting together a whole lot of different jurisdictions, but at the same time, lots of these jurisdictions have rates that are increasing. And numbers like the hospitalizations and the death rates are particularly important. But so here's what's happening. This is a Japanese Sapporo University website. And my collaborators from Canada. And so we've included this this data. So this is basically the data of the new cases. And it's hard to read this scale. So this is 20 cases per 10,000 is at this level, 10,000 people. So I would emphasize that what we should be talking about to people is not the numbers. What we get from the news is, oh, the numbers are down. Or, oh, the numbers are up. Oh, the numbers are up. I mean, news media like to emphasize things, and it's either up or down. And that's the basically extent, or maybe the hospitals are crowded, but it's either increasing epidemic or decreasing epidemic. And no subtlety in the news reporting, and I think subtlety is possible. But let's look here. Here we have the same data, and the US, so we just pick the slope. Now you could pick the slope a slightly different place, you get a different beta, but this is basically your reproduction rate from week to week. These two lines represent 1 week apart, and so we can calculate what the increase is on this log scale. And we can calculate how much it's increasing by. So France and the United States are at 1.4 or 1.46 if you take this particular slope. See, France is having such variation, it's very hard to even fit it to a straight line at the present time, so we picked it a little bit earlier. Japan, which is doing very well at the moment, has a bigger problem, 1.6 per week, worse than the other countries. Now, what you should be telling the people is the rate at which it's increasing. This indicates how much does society have to do. Suppose you have 1.6, and you say, what does society have to do to be able to get this number down to 1? You want to get it below 1, but how do you get it down to 1? And so this is what I would be emphasizing. Also, plotting things on a log scale makes a huge difference. I'll get more into that. Now, the simplest models. So a simple model, so here's a model, and beta is a parameter. Actually, it's a parameter depending on time. N is the generation time, the time from generation to generation, which is quite hard to determine, and I don't have a great estimate for it. And in any case, if I had an estimate for it, I wouldn't have error bounds, because the error bounds would be embarrassingly big. So we're going to talk about two models, and the simplest model, E, is simply this model. Now, I've shown you how beta fluctuates from week to week quite a bit. And anybody who tells me, well, I should include other factors like changes in the susceptible population. Well, for understanding the major countries, it would seem like the fraction infected so far may be below 10%. And so this would make a 10% change in beta. And we just saw how in Iowa, beta jumps from 1.1 to 1.6. The fluctuations in beta are much bigger than the amount that we have to correct this for due to changes in the susceptible population dropping below 1. But we can consider it. But if you want to, look, this model is not being communicated to our population. The people don't know that this is what they should be thinking about. They're simply saying increasing or decreasing. And the rate at which it's increasing is key. So here is an example of from Model E, where we can, here we have an epidemic outbreak, and we're using beta is equal to 2. And then we have a little intervention for a while in the blue, and then the intervention stops. And in America, we would say, oh, the intervention was successful, the epidemic is very low. If you plot it on a log scale, you see that what's happened is the epidemic has been delayed. But it's growing, it's just, there's a gap here. So instead of being here, we're being delayed by about 7 weeks. So the point is, newspapers should be able to tell people what log plots are. Let them get used to them. number of cases being plotted logarithmically, and you wouldn't make this mistake. In the United States, once this thing is flat, you don't care whether beta is below 1 or equal to 1. You being the American population, and you being the governors of states. Now, we can, of course, include susceptibles, and this is a, I guess, somewhat standard Kermick-McKendrick model, not as a differential equation, but as a time step of one generation time. And this is Poisson statistics. So this is the infectious people and the susceptible people. And we want to say that this model incorporates a great deal of what's essential to know about an epidemic. That's one of the messages here. Now, if I give you an epidemic curve, you can't quite calculate what the how the number of susceptibles is varying if you don't know the initial value of susceptibles. So in order to, if you knew beta, to run this model, you need I and S at time 1. And you may or may not have that information. Now, this is simply a model. This is simply saying that you can have models which include variability within the population, such as some people have many more contacts than other people, and we have subpopulations like that. And what you get is you get differences in the epidemic. And the fact is, we don't know how much the contact rate varies from person to person. And certainly not within any accuracy. And until the issue of super spreaders is resolved, it may be impossible to evaluate how important the variability is. It could be that all that counts is people going to big meetings. I mean, mostly what counts is people going to big meetings of people without masks and transmitting the disease. So the point is that adding extra factors increases variability in what you're going to predict for your epidemic. And based on parameters which you don't know the value of. Again, to get data for measles, we had excellent data collected over 30 years. It was not based on what's happening at person-to-person contact rates because there's no way to evaluate that. In any case, we find that our model E+ is right in the middle of the epidemics you would get depending on how you want to say how the contact rate varies from subpopulation to subpopulation. So I want to make the point here that that while it may seem stupid to have a simple model such as our E+ model, the one with the infectious, in fact, you can do a lot of evaluations using this kind of data. So as Robin was talking about, for example, what happens to an island? And so perhaps Bermuda wants to know what's going to happen. And you don't need a model which incorporates Bermuda and all the people in the rest of the world and how this links up together. Bermuda doesn't really affect the epidemic in Europe, but people coming from Europe affect the epidemic in Bermuda, as I think Robin would agree. So, for example, here, if you want to estimate what's your probability of becoming infected during this epidemic, you're going to have certain contact rates. And so you could have gamma J's are your personal contact rates per week. And your chance of getting infected depends on the level of infectiousness in the overall population. So the model E plus could give you the overall level of infectiousness in the population. And this is a satellite equation. A satellite equation is an equation where it depends upon what's happening in the main population, but it doesn't directly affect what's happening in the main population. Whether or not I get infected really doesn't have an effect on the overall United States epidemic. And so you can derive the following result that, so what fraction of the population gets infected during your outbreak? I don't know, but it's going to be some number. Perhaps 20%, who knows? But my probability of being infected is gamma is my contact rate times this 0.2, and we calculate this and we get a probability of me becoming infected. So here we're taking a complicated problem, which isn't in the problem, but we're using the model E plus or E to be able to derive, or just the data, to be able to derive the conclusion. So here I picked on my collaborator, Sana, and said, suppose he has half a contact per week. And suppose 10% of the population gets infected. And what's her chances of becoming infected? Well, it looks like 0.64. So, sorry, remaining. Am I mixing this up? So this is her probability of remaining uninfected. I got mixed that. Okay. This is the problem that Robin was talking about. Number of visitors, this is a different aspect of the same problem. Number of visitors visiting from the main population per period. Now, this could be an island or it could be a nursing home. Once the epidemic hits a nursing home, it seems like it goes through the population pretty quickly. So while you can think about your number of contacts, the number of contacts a nursing home has is much higher. You might have 200 people visiting a big nursing home per week. And some fraction of these, so this means that the nursing home as a whole has 200 contacts, much higher than what you'd expect from an individual. And you can then see that just because of this, the probability of infecting people in the nursing home is very high. Now, I've heard people writing papers about, well, how can we explain the high transmission rate in the nursing homes? And maybe the same people are working at different nursing homes and they're getting infected and carrying the disease from one to the other. Well, that's not necessary. This is simply saying if your nursing home collectively has a large number of contacts, then you're going to be likely to, almost certain, to transmit the disease to the nursing home. So New Brunswick, Canada is where Sana is from. And so it's the same thing, an isolated population. And you don't need a complex model to analyze these things, and you can explain it to the population a bit easier. Now, this is a more complicated situation. So New York, the New York Times asked for predictions. There had been a lockdown, and they wanted predictions on what was going to happen in New York. And they got predictions from 4 different groups. So C is Columbia University, M is MIT, L is Los Alamos Laboratories, and I is a group. And they came up with these predictions as to how the rates would go down. Now, these are deaths, but if we assume that deaths are proportional to cases, over a short period of time of a couple of weeks, then we can think that these are really, think of these as proportional to the number of cases. Okay, who's right? How do you determine who's right? You don't know what the assumptions are. One group said the following: well, we know what epidemic curves look like. They go up at a certain rate and they come down at the same rate. And so it bases prediction based on that, ignoring the fact that this coming down is due to a lockdown, not due to exhausting of susceptibles. Another group might say, well, we think there's going to be a radical cure in the next 5 weeks, and it's going to cause the case rate to drop. We don't know. How do you evaluate these? You might want to throw out a prediction where they're assuming that the case rate is going to be cured quickly, the magical cure will occur, if they haven't revealed this as an essential assumption of their model. So we can use the model E plus to evaluate these. Now, assume that these are moderately complicated models. These are week by week estimates. And so if we wanted to fit, so here, this is basically telling us case rates, but we don't know what the susceptible fraction of the population is. In particular, they're telling us how many cases there are going to be in week 1, but not how many people are susceptible. They don't report that. So the fraction of I over S at the initial time is unknown. And we can try different values. Now, our assumption is that the contact rate after the implementation of the lockdown should remain amount constant. And so here, this is one of these, I don't remember which of these models this is, but in any case, it doesn't matter. But the point is, by choosing different levels of susceptibles, we get different, this is different estimates to what beta will be like. We only need this one number to be able to calculate beta. And so we choose for each model the initial susceptibles for their model, which makes this as flat as possible. Hope you got that. So here, this is 0.1358, and over here we choose it to be 1358, and therefore we have a model. Now, what happens then is once we've chosen this, we can calculate the betas. And for example, if we're trying to model the blue curve, using this beta, we will get the blue curve. So while this came from MIT, if we choose the betas to fit the curve, then we will exactly reproduce the blue curve perfectly. So the E plus model is able to predict each of these if you have the betas and the initial condition. And so this tells us how we pick the initial condition. Okay, so here again, this is the same data. And lo and behold, what we find is that using this criteria, we get that Columbia, Los Alamos, and MIT all have about the same parameters. And over here, the I model drops down and cases go away. It turns out that when you fit beta and the initial conditions, the way you get this is by, and this is remarkable, what the E plus model is saying, the only way you're going to get this curve is if most of the people who are susceptible get in week 1 get infected in the following week. Most of the people get infected in 1 week. And so basically, that means you're going to run out of susceptibles. And the reason you get this result of it dropping down so fast is because there's nobody left in the population who's susceptible. This model, by the way, was popular with the Trump administration. because it said the disease would go away. But the New York Times readers don't know why the disease went away. If you use model E+, you figure it out. So that's showing you that a simple model can address this question. You got 4 complicated models. You don't know what their parameters are. You don't know anything about them, but you can evaluate and see that these 3 models are behaving similarly. And this one is assuming that almost everybody gets infected and the disease dies out as a result. Okay. Let me see. Here, we're using model E+ again. And what we're doing is we have a period of time here where we have a temporary lockdown and we want to see what the effect is. And by trying different levels of lockdown, we get different curves. The real emphasis here, model J is a complex model where you can vary the times in which people are infectious. Some people are infectious early, some people are infectious late. And the contacts vary from group to group. And so you got a lot of flexibility in this model, and yet the predictions are pretty much the same. By introducing these extra parameters, you have a great deal of uncertainty built in. But ignoring it, you get the same, basically the same curves with greater uncertainty here. Now you could say, well, the uncertainty is correct, but you don't gain anything. The point is, by having a model which is very complicated, you cannot explain it to the person on the street. In fact, the model E is basically the only one you can explain to a person on the street. This is the same kind of thing. I won't go into the details, but so basically, we believe that the population should know that the goal is to keep beta below 1 and perhaps far below 1. No news media has talked about this. I shouldn't say that. I haven't heard any news media talk about it. This is not something in daily discussion. We can see that the contact rates are generally below about 1.5. Heuristically, it's what you would expect from the measles, mumps, and chickenpox investigations. And for measles, mumps, and chickenpox, the actual levels of the contact rates were very different from each other. Measles is very infectious, mumps is much less infectious, but still we got the same variability seasonally. So what I would like is if the news media started reporting results on log scales and tell people what it means. People in business see log scales often for economic data. And it's not a hard idea, but I used to think that the Washington Post purposely avoided putting tables on the front page of the Washington Post or graphs because they thought their readers were too stupid on the whole. Now, in the economic section, the business section, there were lots of complicated graphs. But I then realized a couple times when they produced graphs on their front pages, they were meaningless. They were terrible. And it really told me that it wasn't the readers who were the problem, it was the reporters and the editors who were the problem. They didn't understand graphs. So as scientists and mathematicians, we have to feel sorry that we have not communicated to the public the ideas of graphs. So that's it for me, and I will open up to questions. Just unmute your mic and go ahead and talk. Quentin.
Thank you, James. Now I see Jacques already has a raised hand, so I think you can talk, Jacques. You just have to just unmute and you can ask a question. And if you can't, then you can just write it in the chat, and I will ask it for you. Okay. There seems to be a problem with your microphone, maybe, because everything seems all right, but we can't hear you. Yeah. So maybe just write a summary in the chat. All right. So just out of curiosity, in your model J, so can you summarize what model you used? I think it's
Well, we have a model where the number of contacts. One aspect is the number of contacts varies, and so we might have, for example, 10 different groups, and we can set the contact rate to vary from group to group, and so we can have the people with the most contacts could have, for example, 10 times as many contacts as the group with the fewest contacts. And then that group will become infected more quickly, of course. And the epidemic will go through the most infectious people quickly. Another aspect is that you can, in the model, you can say, well, the median transmission time for let's say half the population is 3 days, and the median transmission time for the rest of the population is 10 days, or anything in between. And so the point is that this gives you flexibility. It's a moderately complicated model, but it has the problem that you don't have 30 years of data collected to tell you how much variability there is in the transmission times or in the numbers of contacts. So we prefer to avoid that complexity and hope that you can have a model which you can talk to the staff of the governor of New York and explain to them what's going on. And if you want to figure out what do you need, you should avoid these extra complications, which only produce uncertainty. It increases the uncertainty. Uncertainty in your extra parameters increases the uncertainty in your predictions. So.
Right. I think I see your point. Right. So now we have the question by Jack. So he writes that the model by James is marvelous and could be reached by mathematical teachers in high schools. Could be used.
Exactly. Yes.
Right.
But I would say it could also be transmitted not just in high schools, but on TV, and said in the past week, the number of cases have risen by 50%. And so now what does the population have to do to get that 50% rate down to 0% rate? So it's a multiplicative factor. You don't even have to write it down. You can communicate it orally that there's some factor, and we got to people have fewer contacts in order to get this transmission rate down to 1. Right. And 5 years from now, when the next one breaks out, we have seen that countries like France, which do a great job, forget after 4 months of what to do, and the epidemic just breaks out in huge. The United States should be thought of as a country which, as a centrally operating, it didn't do anything to fight to decrease the contact rates. It said we should go back to work and go back to business. We should go out and eat at restaurants and go to the movies. That was the recommendation of the central government of the United States. And somehow France has wound up with a higher rate than the United States. Now, how is that possible? I don't know. But it doesn't give us much faith in the governments. And it's not just France, it's Spain and Italy. Italy was doing very little testing compared to what they could have done. And well, we'll worry about it when it breaks out. And if they don't look at it on a log plot, they don't know that it is breaking out. If they only look at the absolute numbers, the linear scale. I'm preaching, I'm afraid.
Right. So actually, together with Pierre, we built some maybe not as simple as you preach, but some simple model to identify the daily transmission rate lately. So
my feeling is, if you go to the governor and say, look, here's our model. There's a beta by which this thing is increasing every week. And you, as the governor, have to choose how you want to decrease beta. Okay. Yeah. Now, do you think the governor would understand that? Maybe not. Okay, but his staff would, because he hires maybe intelligent people, and they can understand that there's a multiplication rate. And that's the whole thing about the epidemic that you have to know. And you have to get beta while lockdown well below 1. France got the beta well below 1 during the lockdown period. The United States only got it down to 1. So you see what I'm saying is the model, there's almost no model, but they aren't communicating these simple ideas.
So, okay. So, okay. So another question for Robin. And so maybe in order to scare the politicians, the best thing to do would be to use the first model, the E model.
Yes, yeah, definitely not the E plus model, the E model, definitely.
Yeah. That's a great idea.
Okay.
So, well, thank you, James, for a great talk.
Thank you.
So
delighted to be here.
Yeah. So I think the question time is about to be over. So Jack has a question for Robin. So maybe, I don't know if Robin is still here. So it's
hi there. Hi.
So Jacques' question is so apart from a bravo to James, bravo is in in the Corey paper, there is no clear estimation of the W's. So have you done it from the observed infectious cases? So that's the question.
Yeah, that's a good question. So by the W's, just to absolutely clarify what Jacques means, I guess he means the serial interval distribution. So the probability of serial intervals having different days, as opposed to the length of the window, right? So yeah, so I can talk about both of those things, in fact. So when it comes to estimating the serial interval distribution, probably the paper to read is not Anne Corrie's original paper, but the follow-up paper that we wrote together last year in Epidemics. And in that one, a sort of method for estimating the W's is included as part of the overall framework. It should be said, though, that uses, so it doesn't use that from observed incidence data, but instead it does it from observations for known source recipient pairs. So in other words, you estimate the serial interval from observations of the time interval between a source developing symptoms and a recipient developing symptoms. So the kind of data that you get, for example, in household studies. So yeah, so that was how we included estimation of the W's, or the serial interval distribution, in the framework that we developed last year. And then so yeah, the other thing that it's hard to estimate is the optimal length of that window. So I talked about a time window over which you assume that reproduction number estimates are kind of constant, and then you consider a shifting time window. And knowing exactly what that time window should be is something that I think is an area for future research. So, you know, if you use a very short time window, then you get variations in the time-dependent reproduction number that fluctuate a lot. If you use a very long time window, though, on the other hand, then you don't capture any of the fluctuations in the time-dependent reproduction number at all. And so you want to use something that's kind of in the middle. There are different ways that you can address that question to find the optimal time window, but that wasn't something that was included in the framework that we developed. So essentially what you can do is you can look at different time windows and whether they predict the data that were then observed subsequently if you continue with that value of RT, and then you can use that to pick the optimal time window. So some work's been done recently on that by Crystal Donnelly and Chris Parag at Oxford and at Imperial College London, respectively. So yeah.
May I ask another question about that?
Sure.
When you do your estimation, you get it's not a direct estimation of the. You get a model behind that, right? To compute the probability. So you are estimating some parameter within your stochastic model, are you?
Right, exactly. Yeah, exactly. So in the two parts of the talk, exactly what the model was very slightly different. So in the first half, it was just a kind of basic branching process model, so an approximation to a stochastic process.
Mm-hmm.
And then the second half of the talk, it was this renewal equation model, which also makes a branching process assumption, but yeah, a slightly different underlying modeling framework. Yeah.
Okay, thank you.
All right, so I think it's time to thank again the speakers for the great talks, 2 great talks today. And it's time to close the session. So thank you all for participating. And Jacques, I hope I've been your voice in a good way. Right, so thank you all and see you next time.
Thank you, Quentin.
Yeah, thanks, Quentin. Thanks. And thanks everybody else too.
Thank you.
And thanks, Pierre.
For sure.
Right. Bye.